Hello everyone again, and welcome to this particular video. And here we're going to be exploring the Hall effect, and this Hall effect applies to specific machines dealing with how to determine various variables involving the magnetic fields. And the bell work for this particular video is to first, the lesson is the Hall effect, and the goal is to be able to define and observe an Hall effect, and also looking at how to derive the Hall's voltage. And this follows by comparing the classical versus that of the quantum Hall effect, and finally leading to the conclusion, which is mainly dealing with applications of Hall effect. Now, the defining and observing of an Hall effect was actually determined first by this guy right here called Edwin Hall in 1879, which is quite a long time ago, but it's quite remarkable to see that particular century, which was highly involving the discovery of electricity and magnetism, and saying this discovery was crucial for the behavior of various subatomic particles like electrons movement, which creates electrical and magnetic fields. So the Hall effect is the generation of a difference in voltage, and this difference in voltage across an electrical conductor must be perpendicular to both the electrical current, which is actually moving in a specific direction in the three-dimensional plane, and finally perpendicular as well to the magnetic field, which is represented as B. And this particular, I would say, difference in voltage across the electrical current or conductor is actually caused by the deflection of charged particles or carriers. So let's look at the observation of these, looking at a specific material. The observation being that the electrical field is perpendicular to both the current and that of the magnetic field. So in here we have a three-dimensional planes and axis. In here we have the X, Y, and Z, and now we have a specific material. In here it could be a conductor or a semiconductor, but in this case here we notice that the width of this particular conductor is represented as D, and the thickness of this particular conductor is represented as T. And in here we have a specific current that is passing along the x-axis, and we have this material subjected to the magnetic field that is parallel to the y-axis. So what happens here when you have these two forces or fields acting on this particular material? What happens is that since we see that the magnetic field is along the y-axis and the current is along the x-axis, we see that if we have particles that are contained in this particular material, like for example an electron, which is a charged particle specifically, and we see that the movement is opposite to the current movement, so we see that the velocity d is opposite in direction to the current. And if we have a proton that is contained in that particular material, it means that the proton will be moving in the same direction as that of the current, which is in this case represented as D, and this Vd is known to be called the drift velocity. So looking at this, we see that combining the velocities of both particles here and that of the magnetic field, we generate a force that is acting upwards for any material. So in here, once we see this force generated, we can actually create an electrical field that actually pushes the particles in the upward direction of that particular material right there. And this particular field is in the direction of the VH, and this VH, if you measure it, it means that if you plug in the top and you plug in the bottom of that particular material and you determine the voltage, this is actually VH is called the Hall's voltage, which shows that there is a movement or deflection of the charged particles that creates an electrical field that results in the difference in the potential difference in that particular material sides. So in here, what we see in this case is that both the current and the magnetic field are perpendicular to each other, and the electrical field is actually perpendicular not only to the magnetic field but also in here the current. So therefore, in this case, looking at the particles or the charged particles specifically in this particular particle or material, we see that if we have seas of electrons in here before, after, when you subject this particular material or box here to both the current, which is moving along the x-axis, and the magnetic field, which is along the y-axis, we actually see a movement of those electrons either up or down, which creates a deflection of the particles, and this deflection of particles creates the electrical field, which is pretty much in this case expressed as Ez, which is along the z-axis. So what do you notice here? We see that if it is a semiconductor, we create holes, and these holes are seen in the initial position of those electrons in there. So looking at that in here applied in this particular case for semiconductors, let's move on to focusing on deriving the Hall's voltage. And the Hall's voltage here, which we're going to represent as VH, we actually can determine that in here by first since noticing that the magnetic field is pretty much along the J, which is noticed to be the unit vector for the Y. In this case, we can find the magnitude of B, and to find the magnitude of B, we need to take some things into consideration. We have to consider that if the quantity of charge is greater than 0, in this case, what we see is that there is a drift velocity that will be established in here, which means that the drift velocity of a charge greater than 0 is in a positive direction on the x-axis, and this can be determined by considering the unit vector on the x-axis, which is represented as I. So on the other side here, if we have the quantity of charge to be less than 0, in this case the electron, which means that the electron will be moving in the opposite direction on the x-axis, which means that we're going to have a drift velocity to be negative drift velocity in the x direction, which is represented as the unit vector I. So in here, in conclusion, what we notice is that since the quantity of charge is greater than 0 and the quantity of charge is less than 0, we can actually experience a force that we consider to be in the same direction for both particles. So this is highlighted right there in the particular diagram. And in conclusion here, once you see that this movement of particles that are deflected, we can actually lead to a charge buildup either at the top or at the bottom, depending on how the particular current is moving. So in here, in this conclusion is actually what we've gotten from the initial slide. Therefore, next thing to think about is the charge to potential difference between the plate sides. Now we have two sides that are involved here. We have these sides to be along the EZ axis, which is where the electrical field is generated after the deflection of those particles are established, or charged particles. So in here, what we label as the top side, which is where we connect our first line or meter, is C, and the bottom we're going to express that as A. And in this case, if we have our quantity of charge to be greater than 0, it means that in this case the voltage at C is way greater than that of the voltage at A. Therefore, the voltage at C minus the voltage at A is always greater than 0. That is the conversion right there. And if the quantity of charge is less than 0, it means that in here the voltage at C is less than that of A. Therefore, in this case, the voltage at C is minus that of A, which means that the result must be less than 0. So in this case, the difference in the potential for a quantity of charge less than 0 means that your difference of potential must be less than 0. If the quantity of charge is greater than 0, the difference in potential value must be greater than 0 in order for you to determine what your Hall's voltage is. So in here, what we're going to do is to use this concept here to actually establish when a particle or this particular material is at equilibrium. And once this material is at equilibrium, we can lead in here to the conclusion that the steady state must be F net must be equal to 0. Therefore, the two forces must be equal to each other, which is the magnetic force and that of the electrical force. Therefore, the magnetic force is equal to the quantity of charge multiplied by the drift velocity of any charged particle in that material times that of the magnetic field magnitude. And this is equal to that of the electrical field force, which is equal to the quantity of charge multiplied by that of the electrical field that is on the z-axis. That is one thing you need to recognize, and this is pretty much the direct link to the Hall's field. And this electrical field, due to the charge separation, if you solve for it in this particular expression, the quantity of charges cancels out, which means that the Hall's field, in this case the electrical field, is independent of the quantity of charge. Therefore, this here is equal to the drift velocity multiplied by the magnetic field. So since the movement of charged particles happens on the z-axis, we can express the Hall's field in terms of the Hall's voltage and that of the width of this particular material. So this is a direct link to the material width, and in here we see that all those variables are aligned on the z-axis, where we have the electrical field, which is noticed in that particular diagram, and we have the Hall's voltage, which is shown as the meter that measures the difference between the top and the bottom of that particular material. And finally, we have the width of that particular material, which is represented as D. So if you divide your Hall's voltage by that of the width of your material, you will get the electrical field. So in this particular case, in conclusion here, we have this particular expression which we derived from the equilibrium state. Put that into your particular charged particles electrical field, and you will get your expression in terms of the drift velocity. And in this place here, we have this to be shown as the Hall's voltage to be equal to the electrical field times that of the width, and this is also equal to the drift velocity times the magnetic field times that of the width of the material. So once we have this Hall's voltage actually established, that is pretty much the first phase on determining the Hall's voltage. But this expression can be further actually established by considering the number of charged particles per volume in that particular material. And this here, since we know that we can measure our Hall voltage using that expression and then introducing the number of charged particle per volume, which is going to be represented as N, and N is known to be called the charge carrier's density, we also need to consider the cross-section area of that particular material, which is multiplying the width by that of the thickness of that particular material. And once you have that, then next thing you have to consider is how can you actually use that to determine the current density. And we know that the current density is equal to the current divided by the cross-section area. Therefore, in this case, I divided by dt gives you the current density. Therefore, using the Ohm's law at macroscopic level, in here we can actually express our current density in terms of the charge carrying density and that of the quantity of charge, which is equal to I divided by dt is equal to the n times the quantity of charge times the drift velocity. Therefore, solving for the drift velocity, which is represented as vd, we can actually determine vd to be equal to I divided by all the product of the charge carrying density times the quantity of charge times the thickness times the width. Therefore, in here, if you put this equation here into the Hall voltage, we can actually directly link your material's dimensions to the Hall voltage, and this will result in a value for the expression in here to be VH, which is the Hall voltage, to be equal to the product of the current and the magnetic field divided by the product of the charge carrying density times Q times T, T being the thickness of that particular material. So since we have these two expressions right there, one is associating the width with that of either the electrical field or that of the magnetic and the drift velocity, and using the Hall voltage as well to determine either the magnetic field, the current, the charge density, carrier, quantity of charge, or the width of that particular material. Let's look at the classical versus quantum Hall effect. And looking at this here, once you look at the classical versus that of the quantum Hall effect, we first put our Hall effect on the y-axis and measure the magnetic field to see what the Hall effect is. And what we see classically is that there is a smooth relationship variance in here for the classical Hall effect. However, what we see in the quantum Hall effect is a couple of plateaus right here, and those plateaus has specific fraction constants, either 2, 1, 2/3 or 3/5, and all these here is actually caused by what we know to be called the longitudinal voltage. And due to the longitudinal voltage, we see that why the classical Hall effect actually has a smooth curve that has a proportional variance. We actually see that in this case for the quantum effect, we have a couple of spikes in here, and from the spikes you could see that the Hall effect relationship with the longitudinal voltage shows that the plateau on that particular Hall effect is actually due to the zero voltage at the longitudinal voltage. So in this case here, we can see something quite remarkable due to the cause and effect potentially on quantum states involving various particles that are drifting in a specific material. So in here, what we have in this particular case is an application which is actually found in the Hall's probe, and the Hall's probe has this particular look right here. And this particular Hall effect sensor is actually used to measure the magnetic field of a specific material, which will also call this particular sensor to be called a magnetometer. And this actually is used to determine B. And the big question is, how do you do that? This is pretty simple. In here, all you need to know from the material is the charge density and that of the quantity of charge and that of the thickness of the material, and then you measure the Hall's voltage and that of the current. And once you have those variables established, then you can determine your B, which is the magnetic field, by putting all those variables or solving for B first and putting all those variables into this expression or equation, and you'll be able here to determine the magnetic field of that particular material in question. So that is about it for this particular video. Hope you're able to understand how Hall's effect plays in determining the drift velocity and that of determining the magnetic field of any material when current and magnetic field are applied to a specific material that results in the drift of specific electrons or deflection of specific electrons of charged particles to different areas, thereby causing an electrical field and leading to the variable which is called the Hall's voltage. So that's about it for this particular video. If you have any questions, please don't forget to email me and apply this particular concept to any question that you might have. All the same, stay smart and believe in yourselves.